So we're on to question 4. Now, question 4 comes from David Ball, physical chemistry book. They give you heat capacities versus heat capacities in different temperatures. So at different temperatures, they measured at constant volume. So they took like a steel box, right? And they measured the heat capacity at different temperatures. So they watched how that changed. The rest of this question looks like this. So we'll do part A first. What polynomial trend is needed? Now, I know it says this, but I'm just saying it turns out that a cubic polynomial is more than good enough to get good 9s. You could go to the 4th and get a better fit simply to get the area under the curve for a purpose, because it turns out, and we'll show you this in a minute, to calculate the heat of a process, it turns out that you're going to have to graph heat capacities versus temperatures. And the area under that graph will give you what you need. So part A says, we know that we're going to graph something about the heat capacities and the temperature. We're going to ask Excel to fit that graph in front of us, right-click on it in Excel, and say, fit it with a polynomial. Let's choose a cubic. We'll make this simpler. And we'll integrate that between these two temperatures. So heat capacity by definition, this is how I always start thinking about it. So if I wanted to measure a heat capacity, what I would do is arguably, if I could do a special experiment, I could watch the heat I dump in and watch the temperature change. And let's say that, I don't know, let's say it did this. And so at each point, the slope, each one of these points is the heat capacity at that temperature. The slope of Q versus T gives you C. If you held a gas hostage in a steel box, then you could say, in our example, it's constant volume heat capacity. But let's go ahead, because the question is asking us to calculate Q. Well, this graph is literally the value of Q versus T. We don't have that. But how would we calculate that? So you could get dq equals C in our case at the moment for a steel box. Looks like this. Integrate this. It's path dependent. So there's no such thing as delta Q when you integrate. It's just the value of Q over the path, which was the constant volume process for us here. And we would integrate that from T1 to T2. Now remember, we want that. So we know that we're not going to use this graph if we want to calculate Q by itself. This graph would require you to experimentally know Q already against T because you were solving for C. They reversed it on us. They're giving us the C's, and we're asked to calculate Q. So now we look at this, and we say, where does Q exist in this relationship? It's an integral. And so this, see the D, whatever this is, this becomes your x-axis. And by definition, we talked about this. Whatever sits between the integral sign and the dt term becomes your y. So what this says to me is if I graph this, and whatever this relationship looks like, and I have T1 and I have, T2, the area under the graph of CV versus T will give you heat. So long story short, you're looking at this and you're saying, okay. What I'm going to ask Excel to do, I'm going to graph the given CVs versus T. I'm going to, and in this question, it's what? T1 would be 461 Kelvin, and then later you go up to 917. So you're going to graph your CVs versus this right up from whatever they give you. And you're going to say, look, whatever these two temperatures are, fit this piece, right, from here to here, fit that piece with, I'm suggesting just go with a cubic. It would be more than good enough. So you'll right-click on it. You'll get this equation from Excel. You'll take that, stuff it in as your heat capacity as a function of T, and you'll graph it. So you'll go 917K. And right here from Excel itself, so it'll be AX cubed BX squared plus CX plus D DX. The X, of course, is T. This is what you'll graph. This is for part A. You'll get a number. And that number, let's see if I even have it in front of my face. Interesting point. Do you notice that these has units of, where the hell am I? Joule per mole per K. So when you're done this, you don't carry the units through, but you know that because you started with these units, you know that your final units right here, your heat capacity number. So the heat capacity number you're going to get, it's a positive number. And let me just tell you, and the units will be joules per K. Nope, not per K, per mole. And that number will be somewhere in between. Let's say it's going to be somewhere between 5,000 and 15,000. It's a wide range. So your number is going to be somewhere between here. I don't want to give you the exact number, but it's somewhere in there. So you're looking at something to the tune, 5,000 joules, you could have called it 5 kilojoules. If it was 15, you could have called it 15 kilojoules, not 15,000. But the real number will be somewhere in that ballpark, just to let you know the ballpark range. But notice it's per mole. The question wants to know for this sample of gas. So then what you'll do is you'll take that number in joules per mole, and you'll have to multiply it by the number of moles of gas the question gives you, which is what? Oh, it says 3.1. It says 3.189 moles to get your final answer. Part B. Now notice what we're doing here. Part B wants you to come up. You can't right-click on this and ask Excel to cough up what a lot of textbooks are asking us to do. There's no option for Excel to say, oh, we'll fit it using this relationship. Okay? Excel lets you do the cubic. So what you have to do is under data analysis, this outlines how you do it. For the life of me, I use so little. Barry's computer course does a fantastic job of illustrating how you can use the data analysis tool to fit data using something you want it to get answers. So let me just show you what that's going to look like. But long story short, if you go through this exercise, data analysis in Excel will, this even tells you what you put sort of on your spreadsheet, ask it to fit it this way. It'll give you answers for A, B, and C. So what you'll do for that is you will integrate using what Excel coughs up in this format. And you'll integrate from 461 to 917. So what this is trying to do is, if you would fit your data with a normal simple cubic from Excel, get the area under the curve, you get a number. Go ahead and do the fancier fit that a lot of books ask you to fit it this way. Integrate it, get a number. How does it compare to the number from part A? And to do this, what gets coughed up when you do the data analysis that I just printed out, this is what it looked like. So you graph temperature versus 1 over T squared, 2 columns in spreadsheet, and then you put your C's. You get some summary output. In all of this gobbledygook, the A, the B, and the C term come out right here as the intercept was the A, the X variable 1 was B, the X variable 2 was C. And these are the numbers that I get, 17.4, 0.0067, and then this one was, wow, 121,239. But this is, so I need to see this printout when you guys do your own, right? Something similar. So you go through the exercise I had to do it. So that is question 4.